In modern AI infrastructure, the core unit of performance is no longer the isolated accelerator node. The true bottleneck lies within the distributed execution graph. When a distributed system dispatches work, a single 99th percentile queue delay at one specific node forces the entire array of interconnected GPUs to idle. They are trapped waiting at a synchronization barrier. This failure state has a strict mathematical reality. Accelerator cost scales by the maximum completion time among all nodes. A microsecond delay amplifies into aggregate waste. This exact equation maps to the wireless edge, swapping data center compute terms for radio and edge wait times. An autonomous vehicle missing a strict V2X safety deadline because a roadside edge cache stalled is the exact same cross-layer coordination failure as an idle GPU waiting for a token. When compute, network, and storage contend for shared resources, optimizing any single component locally fails the global objective. Teams are deploying 800 gigabit Ethernet, kernel bypasses like XDP and DPDK, and topology-aware collectives. Yet overall job completion times remain heavily bottlenecked. The existing transport layer mechanisms designed to manage this traffic, like explicit congestion notification and priority flow control, are strictly reactive. They send signals or pause traffic only after a queue has already formed. They have no semantic awareness that a massive all-to-all collective is imminent, or that a data packet carries a strict robotic safety deadline. The Predictive Tensor Control Plane, or PTCP, addresses this gap as a cross-layer coordination overlay. It ingests workload intent to forecast resource demand before traffic hits the wire. By separating predictive intelligence from deterministic fast-path execution, we can extract maximum useful AI goodput out of standard brownfield hardware environments. This diagram illustrates the token routing phase of a sparse mixture of experts model. Dynamic routing creates non-stationary, many-to-many traffic patterns as tokens are sent to specific experts. Simultaneous fan-out inevitably creates an incast event at a specific expert node, overloading the immediate path. The transport layer reacts to this congestion. The switch marks the packets with ECN or triggers a PFC pause to protect the loss-sensitive flow. Because the network is completely blind to the collective's logic, it pauses traffic indiscriminately. Downstream accelerators are forced to sit idle, waiting for the synchronization barrier to clear. The transport mechanisms successfully protect the link from packet loss, but they destroy the application's required execution timeline and strand highly expensive compute capacity. This cross-layer blindness behaves exactly the same way in a high-capacity wireless edge environment. You can have a flawlessly operating Wi-Fi 7 or 5G advanced link. But an agentic safety request sent over that perfect radio link can still easily miss its service deadline. Tracing the failure backward, the bottleneck often forms at the multi-access edge computing node. The required key-value cache state was never pre-staged. Lacking local data, the request is forced across a saturated backhaul to the cloud. This triggers compounding queue and inference delays that nullify the physical speed of the radio link. Upgrading a physical pipe is mathematically irrelevant if edge placement, storage locality, and roaming transitions are not preemptively coordinated with the application's strict deadline. The architectural solution to cross-layer blindness requires decoupling the control loop into two distinct temporal planes. At the bottom is the deterministic fast path. This enforces rules at packet speed using existing, unmodified commodity mechanisms. Rather than replacing the underlying protocols, PTCP directly programs Linux XDP maps, DPDK workers, DPU APIs, and sonic switch routing. Above this sits the predictive slow path. Operating on timescales of milliseconds to minutes, it evaluates time-aligned telemetry across all resource domains. It ingests workload intent, such as scheduled NCCL collectives or V2X mobility trajectories, to accurately forecast demand, doing so without ever inspecting payload content. Candidate actions are then fed through a bounded policy gate, where they are strictly checked against security limits, tenant fairness, and blast radius before deployment to the fast path. Because PTCP acts strictly as a bounded overlay, if telemetry goes stale or predictions fail, the fast path safely fails open, leaving standard routing or local safety logic in authoritative control. Returning to the earlier data center scenario, processing the MOE token dispatch through the PTCP slow path
changes the outcome.
PTCP forecasts the hot expert demand and pre-stages an expert replica before the application ever executes the dispatch. The network flow is successfully load balanced. The incast is avoided entirely, generating 0 ECN marks or PFC pause frames. At the compute level, the synchronization barrier wait time collapses, and aggregate GPU utilization stays high. The value of this architecture is not reacting faster to congestion. It is surgically preconditioning the fabric and compute placement so the congestion event never physically occurs. Validating this approach requires strict operational metrics. The relevant measurements are P99 task completion time, accepted tokens per second, and Straggler wait time reduction, not standard link utilization. PTCP does not alter physical layer encoding. It cannot force a 400 gigabit port to transmit 800 gigabits of raw data. In a perfectly greenfield, homogeneous HPC environment, it does not replace InfiniBand's purpose-built hardware latency advantages. And in wireless edge environments, it never overrides local, independently validated safety fallback protocols for autonomous vehicles or robotics. But the vast majority of AI infrastructure does not operate in ideal conditions. It runs over mixed, lossy Ethernet and heterogeneous edge environments. Deploying a predictive overlay in these brownfield environments recovers massive amounts of stranded accelerator time without requiring wholesale fabric replacement. By aligning application semantics with cross-layer infrastructure controls, the industry can break the optimization ceiling of commodity hardware, securing predictable AI performance from the data center core all the way to the wireless edge.